Hello, everybody, and welcome to this webinar on machine learning. I hope you're all comfortably seated. Perhaps some of you are still working from home, as many of us at JLI are in this pandemic era. Please get comfortable with a cup of warm coffee or tea, lean back and enjoy. My name is Henrik Birk. I am the sales manager at JLI Vision. I've been with JLI for the past 25 years. Yes, actually my entire work career. My background is a master's degree from a local Danish university within computer vision and image analysis. At JLI, I started out as a systems developer, but in the past many years, my focus has been on technical sales. Today, I'll be talking about machine learning and the current use within machine vision. Why is this important to you, you may ask? Because machine learning represents new possibilities to solve quality control tasks that we previously thought were impossible or at best very difficult to solve reliably. The outline of the webinar will be first a brief introduction to JLI and what we do. Then I'll focus on the very basics of machine learning. This is indeed, as I say, very basic, so those that have no prior knowledge can follow as well. Once the overview is in place, I will talk about potential challenges and pitfalls of machine learning and share some of our case stories. Towards the end, I'll talk a bit about where machine learning technologies are heading and what we can expect in the future. The presentation will take approximately 30 minutes, hopefully leaving us a bit time for questions, maybe some good answers. During the presentation, you may write down any questions that you have in the chat box that should be either at the top or the bottom of the screen. So let's get started. Who is JLI Vision, or just short JLI, as we prefer to call ourselves in daily speak? JLI is a leading machine vision systems integrator with our headquarters located in Copenhagen, Denmark. The company was founded back in 1985 by Jørgen Lesser on the right side of the picture. This makes JLI one of the oldest suppliers of systems as a system integrators of machine vision in the world. Jan Christensen on the right side is now a co-owner with Mr. Lesser. JLI design and construct vision systems based on smart cameras through embedded systems to highly complex turnkey application-specific systems. We have delivered systems in many different industries and have extensive know-how about how to make machine vision work in real life. Currently, we're a group of 25 vision experts, many of us with more than 20 years of experience. At JLI, we consider ourselves pioneers trying to extend the possibilities within 2D, 3D machine vision and machine learning. We work with many of the biggest companies in the world and are extremely proud of our track record. Enough about us. What is machine learning? Maybe we should start with a bit of history and definitions to avoid further confusion. There are three topics so tightly related in most people's minds. They are almost always being used interchangeably, but they do not necessarily mean the same thing. Artificial intelligence, machine learning, and deep learning have so many published definitions. As current buzzwords, their involvement in human activities is inevitable and will continue to raise concerns about its benefits to man and society versus taking over human jobs. Artificial intelligence goes back to the dark era of World War II, starting in the 40s and 50s. Artificial intelligence represents simulated intelligence in machines and aims at building machines which are capable of thinking like humans. Machine learning, being a subset of AI, dates back to the late 60s, early 70s, and aims at getting machines to make decisions without being explicitly programmed, learning through data so they can solve problems. Deep learning is again a subset of both AI and machine learning and surfaced around 2006. Deep learning is a machine learning technique that aims at learning features and tasks directly from data. It uses deep neural networks, such as a convolutional neural network, to perform acts such as speech recognition, object detection, and can be applied on images. Over the last few years, every major technology company, Google, Microsoft, Tesla, Apple, have become focused on AI and its potential use. We now see hundreds, if not thousands, of AI-related startups mushrooming all over the globe. At JLI, we mostly operate in machine and deep learning. What are the techniques and methods of machine learning? Machine learning is often divided into three categories: supervised learning, unsupervised, and reinforcement learning. Supervised learning is where a system tries to learn the relationship between input and output based on training data and human feedback. We use annotated data or images as we try to map the input to the desired output. Basically, supervised learning is a predictive model used to predict the future outcome based on historical data. Predictive models are normally given clear instructions right from the beginning, as in what needs to be learned and how it needs to be learned. Typically, supervised methods are segmentation and classification. Segmentation methods are used where we need to identify and localize patterns in an image. Classification methods are used where we typically need to identify a number of known defects, either entire images or smaller portions, clip-outs of the image. Unsupervised learning is where a system analyzes data for trends and patterns without being given specific output variables or human feedback. In other words, the system is not provided with any annotated images. It simply tries to identify recurring patterns in the input data. Typical unsupervised methods are clustering and dimension reduction. Reinforcement learning is where a system learns from time series data to maximize the return on the reward it receives for performing certain actions. The system is usually running in a dynamic environment and learns through feedback provided to it in the form of reward and punishment. The desired behavior is encouraged through rewards, and undesired behavior discouraged through punishment. Reinforcement learning can be model-free or model-based. So, what is the basic difference between what we call traditional machine vision methods and machine deep learning methods? In traditional machine vision, what we try to do is to extract a feature or feature set, and based on these, perform a classification. A simple example would be, is there a car in the image? Using traditional methods, we would probably look for features such as, is there a wheel, a window, a front light, a chassis? Not an easy task to perform with traditional methods. Using simple tools such as edge detection, blob analysis, pattern matching, how do you make sure that these methods will work in any condition? Frankly, it is sometimes difficult to generalize because every problem needs a specific or a new feature, and this will in some cases take time to define in an accurate and reliable way, if it is possible at all. Using deep learning methods, you would probably use a supervised method, classification, with lots of annotated data. Data is fed into, for example, a convolutional neural network that over time will handle the feature extraction and classification and provide an output capable of dealing with variations in the scene and environment. Some of the downsides of deep learning are that you need a lot more computational power than normal, for example, in the form of a graphical processing unit. That you typically need to spend a considerable amount of time annotating defect types. That you do have to acquire the images up front, that you must retrain the network for every new defect or object. Sometimes this is also the case for the traditional methods. Depending on the application, it may tend to be a little less accurate. Most developers use software like TensorFlow or PyTorch as their preferred development environment. At JLI, we use TensorFlow for most applications. Let's look at what the normal process is when you develop a deep learning network. 5 steps cover the usual process. Step 1 is collecting or gathering data. Data collection is the key process in the machine learning space. Based on the problem you're facing, we have to go and grab data possibly from different sources, be it the raw data from 2D images, 3D point clouds, hyperspectral images, or other sensors. This step, gathering past data, forms the foundation of the future learning. The better the variety, density, and volume of relevant data, the better the learning prospects for the network becomes. Step 2 is preparing the data. Any analytical process thrives on the quality of the data used. One needs to spend time determining the quality of the data, understand the relationship between features, and then take steps for fixing issues such as missing data or treatment of outliers. The goal is to extract the essential variables and leave behind or remove non-essential variables. It's a challenging and critical task. Handling missing values or human error in the given dataset will enhance the process and improve the modeling performance highly. Identifying outliers in the given dataset is important because they will lead us to unrealistic results. You may also realize that you have to step back and acquire new data before proceeding. Step 3 is choosing and training a model. This step involves choosing the appropriate method and representation of data in the form of the method and model. The cleaned data is split into 2 parts, training and test. The first part, training data, is used for developing the model. The second part, test data, is used for a reference when testing the performance. The question is, when do you stop the training? In this image, you can see that the results start to converge at the arrow point in the bottom of the image. At this point, it doesn't add anything to continue the training. So this would be a good time to stop. Step 4 is testing the data. To test the accuracy, the second part of the data is used. This step determines the precision in the choice of the model based on the outcome. A great way to test and check the accuracy of a model is to see its performance on the data which was not used during the model building. Our test data from the previous step. This resembles a real-life test on unknown data. Step 5 and the last is improving the performance. Before you deploy the network, often you probably have to improve the performance. This might involve stepping all the way back and cleaning your data once again, or choosing a different model altogether. Perhaps introducing more variables will help augment the efficiency. In this image, we visualize 6 different defects labels via a confusion matrix. On the x-axis are the results, predictions by the network matched against the truth on the y-axis. As you can see, some defects are detected very accurately, while others have really poor accuracy. If you're experiencing poor accuracy, you may need to bring in other sensors or try with an ensemble of dedicated networks. So, when do we use traditional machine vision and machine learning? In recent years, we've seen multiple examples of using machine learning in machine vision. At JLI, we started about 5 years ago and quickly focused our energy on customer control problems. These can roughly be divided into 2 groups, structural and aesthetic. The first group, being structural applications, would be jobs like ensuring that an item has the correct number of holes, measuring the orientation, the presence, dimensions, angles, in other words, geometries. All applications that are fairly straightforward in defining the specifications and applying traditional machine vision algorithms. The second group would be what we call aesthetic applications. Here we try to ensure that an item has a nice surface, color, check scratches, cracks. As opposed to structural applications, it can be difficult to define good and bad specs and define methods, models with traditional machine vision. Machine learning, deep learning, is particularly well suited for these aesthetic applications because they are somewhat more flexible and require less reprogramming if something changes or a new design of the product is made. Some will say that the Achilles heel of traditional machine vision is the rule-based system it follows, which makes foreseeing future issues highly dependent on the developer's ability to include these rules at the design time. Using machine learning, we're at JLI trying to solve some of these aesthetic applications that we previously would have turned down because they were simply too difficult. Well, there's still a lot of manual human visual inspection being used in nearly all types of industries and productions around the world, just waiting to be replaced by automatic control. The basic aim at JLI is to try and catch defects in mass production on the assembly line for our customers. Often our systems will replace human manual control because human manual control has a number of issues. It is labor intensive, making it quite costly. There's a lot of repetitive jobs, which creates chances of mistakes and inefficiency. Poor repeatability and accuracy because of the subjective decisions an inspector must perform. Human control is often slow and a bottleneck because it causes delays in the workflow. The environment may make control impossible, especially in hazardous environments. Machine learning is a great new tool in helping us getting closer to automating some of these human-based controls. At JLI, we operate with a simple rule of thumb. If you can see the defect in the image, you can probably detect it using machine learning. What are the pitfalls and challenges worth highlighting? During the past 5 years, we have developed a knowledge about what to be aware of in the development process. Here are 5 good advices for the good solution. First of all, you need to take care that you design the scene of cameras, illumination, optics in the best possible way. Do not compromise on this point. It will help you at a later stage in the development process. And please note that the test setup must be completely, it must reassemble the setup you obtain in production. If it is any way possible to get a production setup right away, this is the way to go. It saves a lot of trouble. If the size of defects are important, then a basic thing like having the correct zoom in the training data is crucial. Make sure that you gain access to large amounts of data and possibly obtaining more data as you go along if and when this proves necessary. And it will. Again, make sure that you have access to a production setup. Re-annotation will often become necessary. With these amounts of images, in some cases more than 100,000 of images, errors in annotations will occur. If possible, please try to pre-process your images in order to minimize the data amount. Here we see a plastic lid looking at actually inside the lid with the thread visible. The lid may be pre-processed to unfold the inside. It makes it easier to make clip outs and reduce the data amount. For example, focusing on defects in the thread of the lid and not the entire lid. Pre-processing data will also reduce processing time in the final network, something that is important when dealing with inline solutions. Performance, everything from processing time, segmenting. Focus early on how you can parallelize the processing. First case story comes from the wood industry. It's an example of a supervised learning using classification. The object is a glue board where the detection of knots and resin pockets is the goal. As seen in the image, most knots are okay, but some need repair marked by the red circles. I personally cannot tell the difference, and trust me, I've tried, between the good and the bad knots, but it can be taught to a network. Also, the resin pockets must be detected, marked by a green circle. Resin is the sticky thing that comes out of the trees, if you're wondering. Again, these are difficult to locate if you're not a trained operator. Our scanner replaced manual inspection inline, and we solved it by training on more than 20,000 images before reaching approximately 98% detection accuracy. The second case story comes from the glass industry. Again, it's an example of supervised learning using classification. The object here is a glass tube in the hot end of production. We're looking for detection of dirt, metal, speckles. These are detected by traditional machine vision, whereas open and closed airlines are difficult to specify. They appear quite similar, and again, it's a case where it's extremely difficult to see the difference between the two. Closed-end airlines, okay, and seen in the top of the image, and acceptable in production, whereas open-end airlines can pose a threat when the tube is used for medical purposes, shown at the bottom of the screen. Inline glass tube inspection is something that JLI has made for decades. Previously, we couldn't separate open and closed-end airlines before implementing machine learning. Hence, this is a good example of an application where a software upgrade accompanied by simple addition of a GPU made it possible to upgrade our customers with new functionality. We solved it training on more than 10,000 images before reaching approximately, again, 97% accuracy. The third case story comes from the steel industry. The object is a rail in the hot end of production and is an application where we actually started out using an unsupervised method. We thought that we were able to teach an unsupervised network the natural variation of everything that is good, as seen in these three rails. This includes water and scales that may also reassemble what I would personally think, looking at the image, as a defect, but these are okay. But we didn't reach a good enough result and ended up changing the model in the development process. The results from the unsupervised learning ended up being used as input to a supervised classification method. Quite simply, we're looking for any type of anomalies. This may be cracks, missing and/or excess steel, all critical defects that may end up derailing a train if used in track. We solved it first by training unsupervised on more than 100,000 images, and afterwards using a segmentation method, reaching 97% accuracy. Here you see a result from the segmentation. A rail with a crack in the top of the image, and in the bottom, the resulting binary image with the segmented area of the crack in white. The last case story is again taken from the wood industry. It's another example of supervised learning using segmentation. The object this time is a board with glued on veneer pieces that are layered side by side. What we're looking for is the transitions between the individual veneer pieces, and this must be done on different species. The transitions can be so difficult to locate that we as humans have a hard time identifying. First, we see an oak veneer where it becomes gradually more and more difficult to identify the transition towards the bottom of the image in the middle. The network also has trouble in recognizing the bottom part. The next image is of an ash sample. Here, there are three transitions present. The one in the middle is the most difficult and is not completely located by the network, but using some post-processing, we can solve this. The development is currently in a proof of concept phase where good accuracy has been proven. What is the future use of machine learning? A lot of machine vision systems have been deployed worldwide over the past 35 or so years. But there are still many unsolved tasks. especially aesthetic applications. Machine learning is growing at a rapid rate. The availability and focus on acquiring images have exploded over the past years, opening up new opportunities. Most new machine learning applications will require using machine learning in a combination with traditional machine vision to obtain accurate and reliable results. They complement each other. In the near future, we also expect machine learning to make a strong presence within the use of 3D and processing images from multiple angles and point clouds. Anomaly detection is a focus area for especially standardized vision systems, so far not with impressive results. In general, making robust systems based on less data and updating networks in real time will develop and enhance our abilities in the near future. In the medical sector, the question is, how do you validate a machine learning system when lives are at stake? At JLI, we're working on these issues as we speak. So, should you be worried about a future with artificial intelligence, machine learning? As with everything else, we humans find ways to explore new technology. Using machine learning to create deep fake videos may pose a threat at our ability to tell right from wrong. So, as many developers of new technology, we are obligated to use it in an ethical way. I'll give the last word to former President Obama.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you, and stay woke, bitches.
So, thank you all for your patience. I hope this has provided you with some basic insight on machine learning. Feel free to ask any questions. Feel free to email me any questions that you have. Feel free to call me. After the webinar, I will shortly hereafter provide you with a link to download the webinar as a video. So, Mr. Sardella asked a question here. How do you think to validate machine learning in the medical field? We're actually right now, as we speak, working on several jobs within the medical sector using machine learning. And together with those customers, we're trying to define how do we validate these systems in the best way. Typically, the medical sector has more focus on these issues than other sectors. So maybe I will get back to you on that. Anybody else having any questions? Otherwise, as I said, feel free to email me at any time, call. and I'll pick it up from there. Once again, thank you very much for your time and enjoy the rest of the day.